Hi everyone, and welcome back to our next video. So today's topic is on trying to determine where functions are increasing or decreasing, and then we're going to learn about a application of this called the first derivative test. So the first section in this unit, again, the whole unit is really focused on being able to gather as much information as possible about a function's graph so that we can create as accurate of a picture for that graph as possible. So the first section really focused on trying to identify extrema, whether that be the absolute or relative kind, and we really didn't dive too deep into the relative extrema. That's really going to be part of the focus for this and the next section. But we did start to talk about the idea of extrema and where those could possibly exist, and a lot of that's going to pop back up in this video as well. So, but to begin, we're going to start with a look at being able to describe whether a function is increasing or decreasing on a given interval. So if you remember from our previous discussions, we've been talking about this for quite a while now, that the value of a function's derivative is directly correlated or represents the slope of the tangent line at a particular value of x. And again, saying the slope of the tangent line is really the same thing as saying the slope of the original function f of x or whatever it's called. So because of this relationship, again, if I want to describe it notationally, the slope of the tangent line is the same thing as that value of f prime at a particular value of x. So with that relationship in mind, we could use the value of the derivative to help us describe where a function is increasing or decreasing. Knowing where a function increases or decreases is important to us for when we want to determine whether a critical number actually results in a relative minimum or maximum. There's always something special that goes on at those relative extrema, and that's how we can tie in increasing and decreasing with our critical number stuff. So formal definition, a function f is increasing on an interval if for any two numbers x1 and x2 in the interval, if x1 is smaller than x2, so thinking about a number line, that just means from left to right, x1 occurs before x2. So for any two values of x where this is true, it implies that the y value at x1 is less than the y value at x2. That would result in a graph that increases. Now, again, it may not be with a straight line, but just in general, that's the idea. So for any two values of x in the interval that it's increasing on, this relationship will always be true. The fact that the first x occurs before x2, that implies that x's y coordinate is smaller than the second. If a function is decreasing, it's the exact opposite. We still have x1 occurring first. Couldn't flip that order around because, again, we read left to right. But now the y value at x1 is greater than the subsequent y value, and that results in, a decreasing function. So general idea, general definitions for increasing and decreasing, just to formalize it and have us have that idea in the back of our mind. So we could take that concept and the idea that the slope of the tangent line is the same as the value of the derivative to help us connect the function, the original function's increasing or decreasing characteristic with the value of f prime. So when we want to test for increasing or decreasing, we're going to let f be a function that is continuous on the closed interval a to b and differentiable on the open interval a to b. And again, the intervals that we're going to be describing here are, again, the differentiability. We lose the endpoints because of the slope at the endpoints. We can't actually do the slope of the secant line trick and turn it into a tangent line at the endpoints. So when we're actually carrying out this process, or we're testing a function to see where it's increasing or decreasing, there's basically three possibilities, three cases that we can end up with. So first, if f prime is greater than 0, so that would mean positive for all values of x in a given interval, then we say that f is increasing on the closed interval a to b. So again, that is like saying the slope of the tangent line is positive. So if the tangent line has a positive slope, then the curve that it is tangent to on that given interval must have a positive direction to it as well, so increasing. So that is the connection. Positive slope for the tangent means that f is increasing. Second case, if f prime is less than 0 or the slope of the tangent line is negative for all x in the interval, then f is decreasing on the interval a to b. Then the third possibility is that f prime actually equals 0 for all x in a given interval. And again, that can really happen one of two ways. Either the function itself is a constant, like y equals some number, or it's a piecewise function that includes part of that. But there are no other um, functions that lie flat for a given interval besides a constant function. So just keep that in mind. Again, piecewise are really the only other way that can happen. But if it does, then when f prime equals 0, again, that means the slope of the tangent line is 0. And when slope is 0, we always end up with a horizontal line. So that is the third possibility. That means f is constant on that given interval. So again, if you think about numbers, all numbers are classified as either positive, negative, or 0. So each of those cases has a direct result on what the graph of f is doing on that particular interval. Now, one note of notation. If you notice, all three of these intervals that we end up describing about f are actually closed intervals. So there's a bit of confusion sometimes in calculus, some debate that goes on. Some textbooks show these as closed intervals, some show that they are open. There's a bit of discussion around it, but typically what will end up happening, technically we include the endpoints in these intervals. That's why we have brackets, and it's referred to as a closed interval. But typically what will end up happening is when we look at these intervals, a lot of times one of these values could end up being an infinity. So that side would end up being open anyways. But then what happens on the other side a lot of times is we are actually working with special values that other special things are occurring at. And typically you'll see them actually end up being open anyways, just because of how we're using this process. Sometimes the directions will directly say find open intervals on which a function is increasing or decreasing as well. So typically, a lot of times, even though technically they are closed intervals, for what we use this process for, a lot of times actually end up turning into open intervals. So let f be a function that is continuous on the interval a to b. To find open intervals on which f is increasing or decreasing, we've got three basic steps. So first, we are going to locate all the critical numbers of f in our interval a to b. So I actually really don't like that yellow. That's not very easy to see. So remember that our critical numbers from last section, that is all values of x where f prime is either equal to 0 or undefined. Again, those are candidates for where relative extrema or turning points can possibly exist. So those are really important for us because, again, a turning point is where a graph changes direction. So before that turning point, we're all those values in that interval are all doing the same thing. In this case, decreasing, and then at the turning point we switch, now they're increasing. Even on a sharp turn, same idea, decreasing to increasing. So those critical numbers are really important to us when determining intervals for increasing and decreasing. So once I have those, we're going to take the domain of the derivative or the intervals of differentiability. We're going to cut them all up into smaller test intervals. And then we're going to use those and determine the sign of f prime at a test value within each of those intervals. Because the idea is these critical numbers are the only place where the function could actually change directions. So we know that in between those, they all have to do the same thing. Imagine a cubic function that has more than one turning point. So we have two turning points here, and in between negative infinity and this critical number to critical number, and then critical number to positive infinity, those three intervals, the function is always doing the same thing. So we don't have to test all the values in the interval. We can just pick any value inside of each of those and look at the slope of the tangent line. So it's not that the slope of the tangent line is always going to be the same thing between these guys in the interval. Obviously, the graph changes its steepness, but the sign of the slope of the tangent line will always be the same. So it's always positive, always negative, always positive within each of those subintervals. So once we have those signs, we can use those to analyze where the function is increasing or decreasing. And again, that goes back to these three cases. If we get a positive value for f prime, we know f is increasing. Negative means it's decreasing. And then if we got 0, we know the function is constant. That's it. So three pretty easy steps to follow, and we're going to make a little chart to help us with these problems. So for this one, we're going to find the open intervals on which f of x equals x cubed minus 3 halves x squared is increasing or decreasing. So again, step one, we're going to look for critical numbers. And again, that requires us to set the derivative equal to 0 or figure out where it's undefined. So one thing to think about here. So our original function, the domain, is all reals. I know that because it is a polynomial. And remember, with that, we also know that polynomials are continuous everywhere, and they are differentiable everywhere. That differentiability part, remember, the derivative of a polynomial is a polynomial. So this f prime guy also has a domain of all reals automatically. So when we think about our critical numbers, we don't need to waste any time figuring out where f prime is undefined. We can kind of skip over that part. So in this case, when I take my derivative, I'm going to end up with 3x squared. Bring down the 2, that means they cancel, so minus 3x. So now I can set my derivatives equal to 0, and we're going to solve by factoring. This guy has a common factor of 3x, so I get 3x times x minus 1. So I get solutions x equals 0 and positive 1. Those are our critical numbers. So we used critical numbers last section to help us identify absolute extrema on an interval, but this is a little bit different. So we are going to make a similar chart, but instead of just listing values of x, we need to take the domain of the original function. We're going to chop it up into pieces based on these critical numbers. And then our bottom row, it's not going to be the y values at particular x's. It's actually going to be the sign of f prime. So if you struggle with coming up with these intervals, I want you just to simply imagine the x-axis, a number line, and we're going to put the domain of the original function on here. So in this case, it's negative infinity to infinity. And then we're just going to stop at each critical number in between our left and right values. So I'm going to stop at 0, stop at 1. So that breaks it up into 3 subintervals. The first goes from negative infinity to 0, and then we're going to stop at 0. Then from 0 to 1. Sorry, my pen decided to act up this morning. There we go. And then we'll stop at 1, and then from 1 to infinity. Now, barring any kind of weird discontinuities or anything like that, and again, discontinuities should show up when we do the undefined part, the general rule of thumb is however many critical numbers we have, we should typically have one more of those in intervals to check. So 2 critical numbers results in 3 intervals. There are a couple exceptions to that with weird functions that have endpoints that are also critical numbers and that kind of stuff, but typically, we will end up with 3 subintervals if I have 2 critical numbers. So now we're going to pick a test point. I particularly like to write my test points up above, so I don't have to do extra writing. But don't pick really difficult values of x. If you think about what we're going to do, we're going to plug these values into f prime, and depending on what form we want to use, it can be some difficult math. So keep them as small and as simple to use. So try to avoid decimals if at all possible. In this case, it's not going to be. And if 0 is not a critical number, I would always recommend using 0 in whatever interval it falls in. It's the easiest number to do math with. So in this case, the best candidates would be -1. I'm going to do 0.5 for this guy. Again, sometimes it's unavoidable. Sometimes you just have to use decimals. And then we'll use 2 for the last one. Now, for substituting them in, again, I don't necessarily care about the value that I end up with. I care about whether it's positive, 0, or negative. So oftentimes, if you start with a derivative in expanded form, and at some point in the solving process, we ended up with a factored form, like this guy. This is an alternate form of f prime. This is actually going to be the easier form to do this math with, because now all I have to think about is, out of my 2 factors, what are the signs of each of them? So for factor 1 and factor 2, is it a positive times a positive times a negative, and so on? Again, I don't care about the end result number. I care, is it positive, negative, or zero? So in this case, I like to just jot down little signs as we go. When I plug -1 into 3x, I get a negative. And then when I plug -1 inside -1, I also get a negative. So that results in some positive number. I don't care what it is. I know that it's a positive number. I know that at 0, f prime is 0. Again, that was a critical number. Then for 0.5, if I plug positive 0.5 into the first factor, 3x, I get a positive. But inside 0.5 minus 1 is a negative, so that results in a negative value for f prime, which again means any value of x that I pick in between 0 and 1, I will get that same kind of result. Not the exact same number, but they'll all be negative values. At 1, I know it's 0 because, again, it was a critical number. And then the last guy, if I plug 2 in, I get positive out in front times 2 minus 1 is also a positive inside. So we get positive slope there as well. So that was step 2 out of the 3 steps. So step 2, again, we determine the sign of f prime at a test value. So that was this bottom row. So now all we have to do is go through and analyze those results. Now, whether that means you want to add a third row or just simply do it right underneath, that's up to you guys. I'll typically just draw it right underneath. But we are simply taking this result and using that definition earlier to think about what the graph of f is doing. So where f prime has positive slope, like the first and last intervals, we know the graph must be increasing. Where a graph has negative, where f prime has negative values, that means the graph of f must be decreasing. Now, for the critical numbers, we know that they're not intervals, they're strictly values of x, but we do know the same thing holds true, that when a value of x has a slope of 0, the graph actually goes constant for that split moment in time. Or again, if you're thinking about a quantity like velocity, when velocity equals 0, the position of the object stops or is unchanged. It's staying constant for a split moment in time. So if you just look at the arrows of what this table describes to us, you can kind of start to piece together what this graph looks like. Kind of looks like a squiggly cubic graph typically looks like the one that I sketched earlier. And that is in fact what this guy looks like. Now, how deep each one of these curves or changes goes, that's not something we would be able to tell just by looking at this chart, but we can tell that this graph changes direction 2 different times. It goes up, changes direction, and goes down at x equals 0, then goes down and changes direction to go up at x equals 1. So for our intervals, what they're asking us to find here, this function is increasing on the intervals negative infinity to 0, as well as 1 to infinity, and then it is decreasing on the open interval 0 to 1. That's it. So we're just using those critical numbers to try and help us figure out where should we break the interval up to see where could we have possibly changed directions. And just to get this out of the way, not every function will actually change directions at each critical number. It's not a guarantee. Some people think because of the examples that we choose that for the first few problems that they can just automatically assume that it will change directions if you found a critical number. That is definitely not always the case. There are plenty of functions where derivative equals 0 or is undefined, but we do not actually end up changing directions around those critical numbers. So don't get into the assumption game. That'll get you into trouble. All right, let's try another one. So we're going to do the same thing, but now our function is x squared minus 4x minus 5. Now, some of these basic functions, you guys already kind of know what the shape of the function looks like. This is a parabola that opens up. So you guys know the rules for parabolas. All parabolas have one extrema, either a minimum or a maximum. So that would be a turning point where the graph changes direction. So going into this, we kind of already know what we are going to end up finding. But now we can guarantee where that actually occurs at. So same process, we're going to find our critical numbers. Again, domain here is all reals, continuous everywhere, differentiable everywhere. Again, that means f prime's derivative, or the derivative function has a domain of all reals as well. In this case, that equation is 2x minus 4. So we only have to set this guy equal to 0, and that gives us x equals 2. add 4, divide by 2. So we only have one critical number here. So again, if I have one critical number, that means I'm going to take my domain and break it up into two subintervals. So negative infinity to 2, we'll stop at 2, and then 2 to infinity. So good test value, again, if 0 is an option, always use it. So I'm going to do 0 and 3 as my test values. There's not really a factored form. I mean, technically you could factor it, but it's just a numeric GCF, no variable. So it's just as easy to just plug these values in and see what we get. 0 goes in, we get 0 minus 4. That is a negative value. 2 produces 0. And then if I plug 3 in, 2 times 3 minus 4 is a positive. So we know that this function decreases, goes flat for a split moment in time, and then increases. And again, that is the general shape of a concave up or a parabola that opens up. So we know this function increases on the interval negative infinity to 2 and decreases on the interval 2 to infinity. So again, that's something that you guys could have been asked to do back in Algebra 1 or Algebra 2, because we know that it changes direction at the vertex of that graph. And if you remember, we used to have this old shortcut for finding the vertex's coordinates. We do the negative b over 2a, and then we plug that x value into the function to find the y coordinate. Well, opposite of b is 4 divided by 2 times my a value of 1 gives me 2. So this is the old algebraic way of finding the x-coordinate for that vertex. But now we have a new calculus way of finding the coordinates of that vertex, and it revolves around the fact that that is a turning point or a critical number where f prime is equal to 0. So all kinds of neat connections that we're going to be making here between the old algebra way of doing things and then our new calculus ways. All right, so now we're going to take a look at something super important to us called the first derivative test. So between this video right now and the next one to come, we're going to learn two tests, the first derivative test and the second derivative test. Both of them serve the same purpose, but they go about doing it in different ways. But the end goal for these is trying to prove where extrema will exist. And that's why the very last step in this process actually starts off with those words. So the goal is to try and figure out where a function's relative extrema, if it has any, will exist on that function's graph. So the first derivative test uses what we just learned how to do to prove where those points will exist on a function's curve. So the good news is you're literally going to do everything that we just did for the increasing, decreasing stuff. All of that is basically the first three steps of the first derivative test. But at the very end, we're just going to make one extra analysis to trying to determine where these relative extrema exist. So that's the good news. It's not really that we're doing anything new. We're just going to call it something specific and make one extra little analysis at the very end. So the steps to do this. We are going to start identifying critical numbers. We know how to do that. That's pretty simple. Again, that's where f prime equals 0 or is undefined. 2, we're going to find all the test intervals. So again, we're taking the domain and we are splitting it up at wherever those critical numbers are. Step 3, we're going to find the value of f prime at one test value within each interval. We did that already for the previous problems. Then we're going to identify whether the function is increasing or decreasing in those intervals to help us figure out where these extrema exist. Well, we've already done that. So the very last step, this is the only new part, this is the new analysis, is we're going to take where the functions change directions and apply a new name to them. So our relative extrema will exist at any critical number where the sign of f prime changes at the critical number, as long as f of x is defined at that critical number. So this part is really important, okay? So there will be some functions like, let's do 1 over x squared. So the function 1 over x squared has a vertical asymptote at x equals 0. It also has a horizontal asymptote at y equals 0, but that one's not as important to us right now. And the graph looks like this guy. And this is one bad part of improving these videos sometimes. I really hope that's not an example that we're going to do here in a minute. Otherwise, I got to go back and delete this. Fingers crossed. This function goes from increasing on the left half to decreasing on the right half, and it changes at x equals 0. Well, any discontinuities on the graph of f will result in values of f prime that are undefined. So x equals 0 is actually a critical number for this function 1 over x squared. But it's not a point where the function is actually defined. So even though the graph changes direction, it goes from increasing to decreasing at x equals 0, this is not a point on the graph of f, and therefore it can't actually turn into relative extrema. So there's just a tiny little extra bit of analysis that we have to go through here to really be able to put all the information together and figure out where these extrema exist. So this process is going to feel very, very similar to what we just did. But again, I don't want you guys to take anything for granted or assume anything and just automatically jump to, oh, it increases to decreases, so it's automatically a relative extrema. We have to be very careful with our analysis that we don't make assumptions and jump to conclusions. However, it is a very simple, straightforward process that's going to feel very repetitive. But again, we just have to gather all the evidence before we make that final conclusion. All right, so we are going to first start with a little trig function or a combination of trig. So we're going to find relative extrema of the function f of x equals 1/2 x minus sine of x on the interval 0 to 2 pi. So not all of these problems have intervals. Most of them don't. But typically when we have trig involved, you guys will be given an interval because, again, the wave nature, I believe this guy is like a slanted wave curve. But because the trig functions are periodic and they continue to repeat their cycles over and over again, there would be an infinite number of relative extrema that you guys would have to find. So that's typically why you'll be given an interval to start with. So when we go to find our critical numbers, you're only looking for ones that fall within that first revolution of the unit circle. Okay? So let's do that though. Again, step 1, critical numbers. Now let's analyze a little bit about our original function, talk about domain. So 1/2 x, that is a polynomial function. Domain is all reals. Sine of x, trig function. Again, that's the set of angles on the unit circle paired with the y-coordinates at those angles. Every angle has a y-coordinate, so the domain for sine is also all reals. And so when we combine the two, our domain is all reals. There are no continuity issues with either of these functions, so when I take their y's and subtract them, which is how these guys are being combined, there won't be any continuity issues or differentiability issues. There are no vertical tangents on 1/2 x or sine of x, so or sharp turns, anything crazy like that. So the good news is we don't have to worry about anything crazy going on here. Okay, the graph is kind of weird looking, but the differentiability part's important because that means I can just worry about where f prime equals 0. So let's find f prime. So derivative of 1/2 x is 1/2. Derivative of sine of x is cosine of x. So now let's set this guy equal to 0. I'm going to move the negative cosine over. It just makes it easier. I can get it all done in one step. So I get cosine equals 1/2. Again, I'm limited to just one revolution of the unit circle. So cosine is my x-coordinate. X is positive in the first and fourth quadrants. So I don't need to worry about over here. 1/2 is the smaller coordinates. So I want an x-coordinate that's small, y-coordinate that's big. That's the tall, skinny triangle. So that is pi over 3. And then its fourth quadrant counterpart, that would be 5 pi over 3. Again, I don't have to have the whole circle memorized. I just have to be able to recreate the pieces that I need. So those are my critical numbers, pi over 3 and 5 pi over 3. So step 1 is done. Step 2, now we're going to find all of our test intervals. Again, the domain had been all reals, so negative infinity to infinity. But in this case, they are restricting us to 0 to 2 pi. So instead of using the entire function's domain, we're actually going to start at 0, end at 2 pi. So that does restrict us a little bit. So that means our chart's going to look slightly different when we set this up. But then in between those two, we still have pi over 3 and 5 pi over 3. So we have two critical numbers, so we still have 3 test intervals, okay? So step 2 is done. Step 3, now we're going to set up our chart, and we're going to test our values of f prime. So when I said it looks different, it's really just because we're not starting and ending with the infinity. So in this case, we're going to go 0 to pi over 3, then stop at pi over 3, then pi over 3 to 5 pi over 3, stop at 5 pi over 3. Again, we always want to stop at these critical numbers, especially now when we apply the first derivative test, because these could turn into these extrema, and so we want them listed there already. And then our last interval, 5 pi over 3 to 2 pi. All right, so this is going to be a little bit trickier than the increasing, decreasing ones we did before, mainly because it's trig. Trig always makes things a little bit more difficult, but it's still manageable, still possible. So here's my unit circle. So that one tricky part is having to pick out test values. So I always recommend that you guys sketch out unit circles so you can visualize where your angles are. And important here is so that you can actually figure out test values in between your intervals. So for the first one, 0 to pi over 3, I really only have 2 good choices here. It can't be 0 and it can't be pi over 3. So you guys can pick either one in there. In this case, I'm going to pick pi over 6. Okay, I'll explain why in a minute. So that's my first test angle. Then between pi over 3 and 5 pi over 3, so that would be this big section here. I can pick anything in there that I want to. There's some decent choices in there. Again, pick the easiest ones. The quadrant angles are easier coordinates to work with, and you actually have all 3 in there. So you could do pi over 2 pi or 3 pi over 2. I'm going to choose pi over 2, and I'll explain why in a minute, but that's my second test value. And then the last interval goes from 5 pi over 3 to 2 pi, and for that one, I'm going to pick 11 pi over 6. Now, the reasons why I chose those. So when we go to plug these values in, we are going to be trying to figure out whether this quantity is positive, 0, or negative. We know the test values aren't going to produce 0 because that's what the critical numbers were for. So if you ever choose a test value, plug it in and get 0, you either didn't find all your critical numbers and actually happened to find another one, or you just substituted in and made a calculation error. But you should never pick a test value that is correctly producing 0. That's typically a sign that something's going wrong. But because this is subtraction, and it's really a constant minus this value of cosine, you're really just wondering, am I going to take 1/2 minus a bigger number or a smaller number? 1/2 minus a bigger number is going to result in a negative. 1/2 minus a smaller number is going to result in a positive answer. So it's really just a matter of determining, is the x-coordinate at these angles that I chose bigger or smaller than 1/2? So that's why I chose the angles that I chose. Now for the first and last guy, notice that both of those are multiples of pi over 6. I did that on purpose because in the first and fourth quadrant, the x-coordinates are the same thing. So it wouldn't have really been all that helpful to do pi over 6 and then 7 pi over 4, because then I have to think about different angles and their coordinates. So try to keep it as simple for yourself as possible. So at pi over 6, that is the low-lying angle, or the short fat triangle. That is where x is bigger than the y. So that is square root of 3 over 2. So square root of 3 over 2 is bigger than 1/2. So if I do 1/2 minus root 3 over 2, I am going to get a negative answer. At pi over 2, I chose pi over 2 because on the y-axis angles, the x-coordinate is 0. So I know that's really easy. 0 is 1/2 minus nothing is 1/2. So it's going to be positive. Now, pi wouldn't have been much more difficult, but then pi requires actual calculations. -1, 1/2 minus -1 would still give you a positive answer because of the double negatives. Then for the last guy, again, 11 pi over 6, it's going to be the exact same result as pi over 6 because these guys have the exact same coordinates. So I know the result is exactly the same. You'll see that a lot with these trig functions that because of the cyclical nature, oftentimes what happens in our first interval tends to repeat itself in the last. Not always a guarantee, but it is a common pattern that you see pop up with trig functions. All right, so we just did step 4. So we identified the increasing, decreasing nature. Or, well, I'm sorry, we're going to do that right now. So f prime is negative, which means our original function f is decreasing. We go flat. F prime is now positive, so we are increasing. We go flat. And then f prime is negative, so we go decreasing again. So that is our step 4. Now our step 5, so everything up to this point we did in the previous problems. Took us a little bit longer because of the trig, but this is no different than just finding intervals of increasing, decreasing. If I change the directions right now, I don't have to change any of the work. I would just now go and write my intervals for increasing, decreasing. The only difference now is that now we're going to look at the pattern and the change in these guys and identify our relative min and our relative maximum. Not every function has both. Some functions have neither of these. It's up to us to determine what exists. So for a relative minimum to occur, the original function must go from decreasing to increasing, and in between, f prime must equal 0 or be undefined. So again, that would be a smooth turning point at a minimum or a sharp turn point at that minimum. But in both of those cases, the original function is defined at that value of x. And our original function has a domain of all reals, so we don't have to worry about any discontinuities here. So that 1 over x squared possibility does not exist with this particular function. So that means I do, in fact, have a relative minimum at x equals pi over 3. Now, to find the y-coordinate, we have to go back and plug that guy in here. So that would give me 1/2 times pi over 3 minus the y-coordinate at pi over 3. Well, pi over 3 is the tall, skinny guy. Tall means big y-coordinate, so that would be 1/2 of pi over 3 would be pi over 6. Sine of pi over 3 would be square root of 3 over 2. There's not a pretty way to write this guy, but that is the exact form of that y value. Then for relative maximums to occur, the original function must go from increasing to decreasing, and that same condition for in between has to occur. So again, we're changing directions. So in this case, we do have a relative maximum, and that is occurring at 5 pi over 3. So we're going to plug that in to the original function. So we get 1/2 times 5 pi over 3 minus sine of 5 pi over 3. Well, 5 pi over 3 is down here. The only difference between that and positive, or 1 pi over 3, is that now the y-coordinate is negative because it's in the fourth quadrant. So this gives me 5 pi over 6 minus negative square root of 3 over 2, or plus root 3 over 2. So that is our y-coordinate. So we know that if we were to graph this guy in Desmos and look at it on that interval, we would see those two turning points, and now we know their exact coordinates. So this might not seem like a earth-shattering revelation for the new process, but one thing to keep in mind throughout all the math classes that you guys have had before in the past, for a lot of these functions, especially anything beyond a quadratic, once you get into x cubes and beyond, we never really asked you guys to find coordinates of where these functions change directions. We asked you to be able to look at a graph and be able to describe where they change. But as far as just giving you the equation and then going out on your own and trying to figure out those turning points, especially when it comes to rational functions, those are really tricky ones. When I've got a rational function with a slant asymptote and the graph is pinched in between these two, you are never held liable for finding the coordinates of those because it's impossible just with algebra. Short of plugging in every possible value of x and looking for the mins and max, it's not possible to do that math without the use of calculus and this process with this first derivative test. That is really the big change here. It opens up, this test opens up doors to other functions that we are now able to calculate this information for. So it helps us gain a clearer picture of what their graphs look like. All right, let's take a look at one more example. Same exact process. Again, notice the directions. We're just asked to find relative extrema. So again, I mentioned earlier that the next section in this unit, we're going to look at another kind of test that uses another characteristic of a graph to try and determine what kind of extrema exist and where. So after we learn that guy, you will see problems with these same directions. And once we know both, it's really going to be up to you to determine which test that you would like to apply to try and find those relative extrema. But you do have to kind of train yourself that it's not going to come out and directly say, use the first derivative test, use the second derivative test to find relative extrema. It's just going to tell you to find them. They don't really care about how, they just want you to be able to do it, okay? So when we see these directions, for right now, the only test we know is to use intervals of increasing, decreasing to determine where the function exists, or excuse me, where the extrema exist. So let's find our critical numbers. Now this one's pretty interesting. This graph is kind of neat to look at. All right, so let's think about domain here real quick. So again, critical numbers, we need to think about f prime. But first, let's talk about the domain. So on the inside, we have a quadratic function, x squared minus 4. So that guy has no issues with being able to substitute values of x in. But when we talk about these fractional exponents, those can always be tricky, and it depends on the denominator. The top exponent doesn't matter what it is. I can raise any number I want to any whole number power. I can square anything, cube anything, fourth anything, doesn't matter. But the bottom number represents a radical or a root, and that does have issues. Remember that when we have an even number on the bottom, that is an even root. That is where we get into issues. You are not able to find a real number answer to an even root of a negative value. But if it's an odd root, like we have in this case, then there are no issues. So really the only issue with those radicals are the sign of the numbers. We can't take even roots of negative values. We can do it with 0 and positives, just not negatives. So while this one doesn't actually end up being any kind of issue, and we still in fact have a domain of all reals, it's still not something that you want to assume or take for granted. When you see a fractional exponent, do some analysis in your head or on paper to make sure that you're okay to proceed and not have to worry about anything funky, okay? So we have a domain of all reals. Continuity and differentiability, those are a little bit tougher questions to answer here without running into or having to do some more analysis. Now, continuity is not that hard. If the domain is all reals, again, barring any kind of piecewise or rational function, which we don't have a negative exponent here, so it's not possible for us to create a domain, or excuse me, a denominator of 0, we don't have any continuity issues either, okay? So this one's pretty straightforward. Every value of x that I substitute in, it's going to produce a real number, no holes that we have to skip over, no asymptotes, nothing crazy. Differentiability, though, that one, we can't just look at this guy and tell. Again, the issues that pop up with differentiability are vertical tangents and sharp turns. Those are not two things that you will know whether they exist or not without doing some analysis of the graph. So, or in this case, we could do some analysis of our derivative, because again, whether a function is differentiable or not is a question of the domain of our derivative function. So let's go ahead and find the derivative of this function. This would be a chain rule problem, has to be, because I have an inside here of x squared minus 4, whose derivative is 2x. So my original function can be rewritten as u to the 2/3 power. So if that's how I interpret this, then my f prime would be 2/3 u to the negative 1/3. And this is where we're going to create an issue. So as soon as I see that negative exponent, that means that that quantity really belongs in the denominator, which means we have a potential to create 0 in the denominator, which could cause issues with the domain of this derivative function, which in turn cause issues with differentiability in the original function. So it's kind of a chain reaction here. and then times u prime. No, that wasn't a pun for chain rule, but happy accident. So now when I clean everything up, the u to the negative 1/3 power is going to go in the denominator with 3, and that leaves me with 2 times u prime up top. So 2 times 2x leaves me with 4x. And then on bottom we have 3 times x squared minus 4, now raised to the 1/3 power. That is my derivative function. So now if I think about the domain of this guy, again, my denominator, it is possible for this guy to equal 0. So I'm going to do that scratch work over here off to the side. If I were to try and set that guy equal to 0, multiplying by 3 doesn't really matter. I can divide that away. So the only way that the whole thing is equal to 0, the 1/3 power I can just get rid of by cubing everything. And essentially, it really just means the inside has to be equal to 0. Well, x squared minus 4, that's x squared equals 4. And we know that that will produce plus or minus 2. Those are critical numbers. Those are values of x that will make the denominator equal to 0, and that's what we can't allow happen. So those are values of x that we remove from the domain of our derivative. So this function is not differentiable everywhere, okay? We can say, though, with certainty, because we just did this process, that it is differentiable everywhere except x equals positive or negative 2. Now, that doesn't mean that we couldn't still have relative extrema there, because again, it's continuous everywhere and has a domain of all reals. So remember, what this does mean, though, is because it's not differentiable, that means that the graph could potentially have either vertical tangents at x equals positive or negative 2, or sharp turns of one of the two varieties. So it is still possible to have relative extrema, because it could end up being one of these guys. Now, so that takes care of one kind of critical number. Now we need to take care of the other kind where the whole derivative equals 0. Well, remember, for an entire fraction to equal 0, we just need the numerator to equal 0. As long as it doesn't also make the bottom equal 0, we're okay. So in this case, 4x equals 0 produces x equals 0 as a critical number as well. So there are 3 critical numbers for this function. So again, thinking about our test intervals from negative infinity to infinity, again, goes back to our domain of all reals, I would be stopping at negative 2, 0, and positive 2. So I have 4 test intervals to work with for this guy. So let us set up those intervals. So I'm going to go from negative infinity to negative 2, stop at our critical number, negative 2 to 0, stop at the critical number, 0 to 2, stop the critical number, and then 2 to infinity. So let's pick out test values now. Again, keep it simple. So let's do negative 3, and then negative 1, and 3. So again, we don't care about the value of f prime. We care about the sign of f prime. So when you deal with fractions, remember the value of the sign of the entire fraction is really just a matter of a ratio of their signs. So a positive over a positive, or a negative over a negative, both of those results yield a positive overall answer. But then if it's a difference of signs in between, difference of signs, positive or negative on top and bottom, that will always yield a negative. So I don't really care what these numbers end up being, just is the top positive or negative, is the bottom positive or negative. So don't waste time with things that remain constant. For example, multiplying by 4 doesn't really change the sign of a number. Multiplying by 3 doesn't really change the sign of the number. So these problems take long enough, so you want to be efficient with your time. So I'm just going to stick my test values into x and inside of here, and that's all I'm really going to worry about. So x being negative 3 gives me a negative up top. X being negative 3 in the bottom, there are some calculations I have to do here. I get positive 9 minus 4, which is a positive, and the cube root of a positive is a positive. So a negative over a positive gives me a negative for the overall value of f prime. At negative 2, we know that the original function, the derivative function was undefined. Same thing at positive 2. That's why they were the critical numbers in the first place. Then -1, same process. I get a negative up top. But now on bottom, -1 squared is 1, and 1 minus 4 is a negative, and the cube root of a negative is still a negative. So we end up with negative, oops, excuse me. Sorry, my tablet went berserk there for a second. We get a negative on bottom, negative over negative gives me a positive value for f prime. 0 produces 0 at f prime. That's why it was a critical number. Now when I plug 1 in, the top for this fraction now is going to be positive. And plugging +1 in the bottom is going to give me the same result for the bottom as -1 because of the x squared. So positive over negative gives me a negative. And then for the last one, 3 going up top is positive. 3 squared is going to give me the same result on bottom as -3. So positive over a positive gives me a positive result. So now let's talk about directions. What's the graph doing? So f prime is negative, graph is going down. Undefined, I don't know what happens just yet, okay? We're going to figure or piece it together, but for right now, undefined, we can't really describe what the graph looks like. We know it's either a vertical tangent or a sharp turn. And then the second half, because now we have positive for f prime, now we are increasing. As soon as I have that information, I know which one of these results it is. It cannot be a vertical tangent if the graph changes directions. Again, a vertical tangent is where I go from increasing. I increase so quickly I approach infinity with the slope, and then I slow down how I'm increasing, or vice versa. If it was the other way, decreasing so fast I go infinite, negative infinity for a slope, and then we slow down with our negative slopes. So, but in those cases, it's still always going to have positive slope, positive to positive infinity, and then smaller positives, or vice versa with the negatives. But because I change directions, I know that the graph has to have a sharp turn. So the graph is going to look like one of those little bird graphs that I've described in past videos. So we do have an extrema here. In this case, we actually have a relative minimum extrema. Now for the next one, 0 slope means I go flat for a split moment in time. Negative slope means I'm decreasing. This is a smooth turning point. In this case, I'm going to have a relative maximum at x equals 0. But now I'm undefined again. So again, my options are the same. We have a little bit more information now. So we know that it's not going to be this vertical tangent option. But I'm going decreasing again, increasing after. So once again, I have a sharp turn. Now again, not all sharp turns look like this. Could actually be flipped upside down. But in that case, I would be increasing first, then undefined, and then decreasing. So that's not the order that I have here, which is how I know that this is another sharp turn relative minimum. So now let's go back and find the coordinates of these. So as far as relative minimum go, I know I have one at x equals -2 and x equals +2. Let's find the y coordinates for those. So if I go back, positive or -2 squared is going to give me 4. So both of those are actually going to give me 0 for the y coordinates. That wasn't too bad. And then when I plug 0 in, sorry about that. When I plug 0 in for x, 0 minus minus 4 is -4. So then we have to do some calculations there with the exponents. If it's possible to take the root, taking the root's usually the better route first because it's going to make everything smaller. But in this case, -4 doesn't have a cube root. So if I don't have that, then we're actually going to leave it in radical form. So let's do the top guy. -4 squared is +16, and then the cube root of 16. We can simplify that because 16 is actually 8 times 2, and 8 is a perfect cube. So the cube root of 8 turns into 2 on the outside, and then we get a cube root of 2 left over on the inside. So in simplest radical form, we get 2 cube roots of 2. So that is it. Now, if I were to graph this guy, you will see that it pretty much looks just like what we just described. Let me clear all this stuff out. So we have x squared minus 4 to the 2/3 power. So we have a decreasing function till we get to -2, and then we have a sharp turn, again, a non-differentiable point because the slope there goes from really steep negative to really steep positive in an instant, and that doesn't happen naturally. So again, that's the non-differentiable point, but it is continuous there, so that's why we still have an extrema. And then you can kind of see this is basically what we showed. It goes from increasing to decreasing, but with a smooth change where we have a slope of 0, and then another sharp turn from steep negative to steep positive instantly. And that's what creates that second sharp turn. But that is exactly what our table described. And hopefully, as you guys get more experience with these, you'll start to be able to piece together what these graphs look like even before we actually graph them. That is it. Those are our relative extrema.